All right, welcome everyone to our a TCS plus talk. I'm very pleased to introduce Jinyoung Park. She's currently a visiting assistant professor at the Courant Institute at NYU, and then she'll also start a permanent tenure track as assistant professor position there as well. She has done multiple postdocs, including time spent at Stanford, time spent at IAS, and her PhD was from Rutgers. And she works broadly on things like probabilistic combinatorics, asymptotic enumeration, and a graph theory. And she will talk to us today about thresholds. Take it away.
Thank you very much for this invitation. So yeah, today I'm going to talk about thresholds, and usually I take questions in the middle of my talks, and I love being interrupted in the middle of my talk, but because this talk is a little bit shorter than the usual talk, it's going to be 45 minutes. So still, you're very welcome to ask questions, but if you think maybe your question will take some time to be answered, then you can keep that until the end of the talk. Okay, so in this talk, this is my plan. In this talk, I'll introduce the Kahn-Kalai conjecture, which is a central conjecture in probabilistic combinatorics, and then we're gonna discuss our results related to this conjecture. And for that, we first start with a brief introduction to random graphs, just to begin with a concrete picture in mind. And also historically, random graph theory was the starting point for our story. Well, later we'll see that the setting of our work is much more general. So let me start from random graphs. So yeah, here we use GMP for the notation of the random graph, and so here GMP is Erdős-Rényi random graph, and this is the definition. So our vertex set is this bracket n, which is the set of integers from 1 up to n. And here we think n is finite, but this is very large. So usually n is like 1 million, 1 billion. It's a very large number. And so because we have n vertices in our ground set, and those vertices are fixed, and because we have n vertices in our ground set, so we have n choose 2 potential edges, and each potential edge is included with probability p independently. And here, this probability p is in our setting, this is usually a function of n, and which tends to 0 as n tends to the infinity. So this p is usually like log n over n or 1 over n. So this is a function of n that tends to 0 as n tends to the infinity. So here is a little example of GMP. So here, let's say n is 3 and p is 1/2. So that means we have 3 vertices in our ground set, and those vertices are labeled. So let's say they are 1, 2, 3. And let's say p is 1/2. So this means we choose each edge with probability 1/2 independently. So that means we have those 8 graphs in our sample space, and each graph has probability exactly 1 over 8 because each edge is chosen with probability 1/2 independently. So this gives us the uniform distribution among all of the possible 8 graphs in our sample space. On the other hand, as we adjust the value of p, our probability distribution changes. So for example, if p is something very small, like 0.01, in this case, those sparse, so this means each edge is present with very small probability. So in this case, the sparser graphs are much more likely, but the denser graphs are much less likely. On the other hand, if p is something closer to 1, let's say this is 0.99, in this case, each edge is chosen with a high probability, so that with a large probability. So that means in this case, the denser graphs are much more likely and the sparser graphs are much less likely. So as you see, GMP is not a fixed graph, but this is a probability distribution defined on the sample space that consists of all different types of graphs. So it makes sense to ask questions such as, what's the probability that GMP is planar? Or what's the probability that GMP is connected? And of course, the answer depends on the value of p. And let me emphasize again that p is a function of n. And when we ask those questions, we are not exactly interested in finding the precise value of the probability. Rather, we want to find out what's the typical behavior of GMP. So given the function of, given the value of P, so if we sample a graph, given the probability distribution, what is the typical behavior of these samples? So that's what we're interested in. And for that, we're going to use the term with high probability. And when we say GMP does A with high probability, then that means the probability that GMP does A tends to 1 as n tends to the infinity. So this was the definition for GMP. And do you have any questions about this definition? Because I don't want to lose my audience in the first page. So if you have any quick questions about the definition, then please feel free to ask. Okay, then let me move on. And let me introduce the evolution of GMP. So one striking thing about GMP is appearance and disappearance of certain properties are abrupt, and this gives us the notion of thresholds. So here, let's think about the evolution of GMP. And when we think about this evolution, that means we think of GMP as we add edges one by one at random. So that means when P is 0, then all of the edges are absent. So we have this state. We have this empty graph. On the other hand, when P is 1, then all of the edges are present. So we have this complete graph on n vertices. And then we think of GMP as we increase P from 0 to 1. So we see that as we add edges one by one at random. So in the first step, we have a graph on n vertices with one edge where this edge is chosen at random. And in the second step, we have a graph with 2 edges. And then as we go on, we have more and more edges. And at the end, we have all of the edges. And in this model, one prototypical question about that shows the evolution of GMP is, threshold phenomena of GMP is this. What's the typical maximum size of connected components of GMP? And in this case, what is well known is if n times P is slightly smaller than 1, so 1 minus epsilon, where epsilon is a fixed constant. In this case, all of the components are small. So the maximum size of connected components is in the order of log n. So this means we ignore constant factors. This is in the order of log n, which is much smaller than the number of vertices, which is n. On the other hand, if n times P is slightly larger than 1, then suddenly we see a giant component whose order is as large as n, so which is the number of vertices. So of course, this means we ignore the constant factors and we just focus on the order. Anyway, so in this sense, we can say that P equals 1 over n, where like this 1 over n, this is the threshold for GMP to have a giant component, because the behavior of the behavior of GMP in terms of having a giant component shows this abrupt change around P equals 1 over n. And this is, as I said, this is just a prototypical example, and there are many other interesting properties where we see this threshold, we see this abrupt change of the behavior. So naturally, it became a central interest in probabilistic combinatorics to find thresholds for various properties. So here I put some of the past results on finding thresholds, and I'm not going to read all of the results in this list, but I wanted to show my audience that, so here we do have a lot of results in this direction, and so there are many people who have worked on this direction of the research. And when you see this list, you'll find that the study has been done mostly for specific properties. So people have worked on finding threshold for example, for the connectivity, or for having a long path, or for having a Hamiltonian cycle. And so all of those studies are about specific properties, but later we'll see, I'm going to introduce the Kalai conjecture, and this conjecture is that this is about having like studying thresholds in more like in more general context. So it's not about for specific properties, but in general, can we give some good bound on the location of the thresholds? So that's what the Kalai conjecture is about. Anyways, okay, in the next part, I'm gonna give you more rigorous notion of thresholds, but do we have any questions so far? Do we have any quick questions so far? Okay. Then, so to introduce the notion of thresholds, let me start from some basic definitions. So our theory is not just for the random graph, but this is for any finite set. So here we use X for a finite set and 2 to the X, as usual, 2 to the X for the power set of X, which is the collection of subsets of X. And we are going to use mu p for the p-biased product probability measure on 2 to the X, which means for any subset A of X, mu p of A is defined to be p to the size of A times 1 minus p to the size of the complement of A. And we are going to use xp for the random variable whose distribution is mu p. So very simply speaking, xp means the p random subset of x, which means we pick each element of x with probability p independently. Then you can easily see that for any given subset A of x, the probability, when we pick each element with probability p independently, then the probability that the set we chose is A, is precisely p to the A times 1 minus p to the size of the complement of A. Because we want to choose all of the elements in A, and we want to avoid all of the non-elements of A. Okay, so XP means that, and as I said, this is a generalization of the random graph theory, and then we can see why. So in the first example, let's say that X is n choose 2, which is the collection of edges in the complete graph Kn. So here Kn means the complete graph, which means we have n vertices and then all of the edges are present. So this is, I don't know how to draw a complete graph. Anyway, so if we take X to be the collection of edges in the complete graph Kn, in this case, what is XP? XP is just a GMP because we choose each edge with probability P independently. So in this case, XP gives the Erdős-Rényi random graph model, or we can view it as edge percolation on the complete graph Kn. And of course, here we do not have to stick to the complete graph Kn. So whatever host graph we have, then XP just gives us the edge percolation model on the given host graph. So we can take the host graph to be a grid or whatever we want. And another example is if we take X to be the collection of K clauses from n variables, in this case, XP can be viewed as a random CNF formula. So which is another interesting object in computer science. And the next thing that we are going to introduce is an increasing property. So in the previous part, we said that we saw a prototypical example of threshold phenomena of GMP, and I said there are many other like interesting properties that shows this threshold phenomena. And to generalize those interesting properties, we introduced the notion of an increasing property. So we say this calligraphic F is an increasing property if this satisfies the following property. This means whenever we have a set that contains a member in the given increasing property, then this set is also contained in the increasing property. So that means if we draw a picture of 2 to the X in this way with the natural process structure, so that means we have the empty set at the bottom and the entire set on the top. So that means in the first layer, we have all of the singletons, and the second layer, we have all of the double tones, etc. And in this case, the picture of an increasing property looks like this, what's on the screen. So that means whenever we have a set A, and we have a member contained in F, then everything that contains the given element A is also contained in F. So this is a picture of an increasing property. And then what are the examples of an increasing property? So if we think about the first example, the random graph example, in this case, the property to be connected. This is an example of an increasing property because, so that means because whenever we have a connected graph, then every graph that contains this connected graph is also connected. So another way to say an increasing property is we can't destroy this property by adding an element. So in that sense, connectivity is an example of an increasing property, and another example is to contain a triangle. Because again, once we have a triangle, then we can't destroy this property by adding an edge. And in the second setup, when we view XP as a random CNF formula, in that setting, the property to be not satisfiable, this is another example of an increasing property. So this was all of the basic definitions. And do we have any questions about this page? Because again, I don't want to lose my audience in the definition page. So please ask me any questions about the definitions. Okay, then let me move on. Then let me introduce thresholds. A well-known fact is that for any increasing property F, so as long as this is not the empty property or the entire property, mu P of F, which is by definition the probability that our random variable XP satisfies the given increasing property F, this is continuous and strictly increasing in P. So one example is this. Let's say that F is the connectivity. I'm just giving you an intuition about this. So let's say F is connectivity. Then in this case, what's the behavior of mu P of F, or what's the probability of XP satisfying the given increasing property connectivity? Here XP is GMP. So if P is 0, then in this case, all of the edges are absent. So in this case, the probability that G and P satisfies the given increasing property, which means G and P is connected. And of course, this probability is 0 because nothing is there. And on the other hand, so that means in the graph below, we are here. When P is 0, mu P of F is 0. On the other hand, when P is 1, in this case, all of the edges are present in GMP. So that means the probability that GMP is connected, this is precisely 1, because this is always connected. So we are here. And then this fact says that as we increase P from 0 to 1, the probability that XP satisfies the given increasing property also increases from 0 to 1. And this function is continuous. So because if once we admit this fact, then because this function is continuous and strictly increasing in P, so we know that there must exist something called PC of F, for which mu P of F is precisely 1/2. And this PC of F is called the threshold for the given increasing property F. So simply speaking, the threshold means if we are below this threshold, then it is unlikely. So this means if we are below the threshold, then mu P of F is small. So that means it's unlikely that XP satisfies the given increasing property F. On the other hand, if we are above the threshold, then that means mu P of F is large, is close to 1. So that means it's more likely that our random variable XP satisfies the given increasing property F. So this PC of F really means where the phase transition happens for the given increasing property F. And if you're familiar with the random graph theory, then probably you have seen the Erdős-Rényi threshold function, which is defined as below. And so if you're more familiar with this threshold function, then let me note that if we define PC of F in the way here, then this PC of F is always on Erdős-Rényi threshold. So this is given by a theorem of Bolobashi and Thomason. So that means now we can treat PC of F as just like the Erdős-Rényi threshold function, P0, which we usually call P0 or whatever. Anyway, so from now on, we're gonna treat PC of F as just the usual Erdős-Rényi threshold function. So yeah, so this was the definition for thresholds. And do we have any questions about this notion? Okay. And there are two interesting directions of study of thresholds. The first direction is what we are interested in. So we're interested in the location of thresholds. And as we saw before, historically, most of the interesting work was on thresholds for specific properties like having a Hamiltonian cycle or being connected. And the Kahn-Kalai conjecture suggests a general bound. And as a preview, let me just give you a brief impression about the Kahn-Kalai conjecture. So given an increasing property F, we are curious about finding the location of its threshold, PC of F. And usually this is very hard to find. But there is another parameter which we call PEF. This is called the expectation threshold, and we'll see this in the next part. Anyway, there is something called PE of F, which is usually easier to find. And this is always a lower bound on the threshold. And then the Kahn-Kalai conjecture says that this easy lower bound, the expectation threshold, is actually an upper bound on the threshold times a tiny error term. So as I said, because this expectation threshold is usually much easier to find, so this conjecture implies that the hard-looking threshold can be easily estimated by this much easier parameter. So this is why this conjecture is so strong. So this is the direction that we're interested in. And the second direction is called the sharpness of thresholds. And so roughly speaking, sharpness means how steep this function is. Or in other words, if we want to reach from epsilon to 1 minus epsilon, how long does it take? So what's the length of this interval? This is called the sharpness of thresholds. And again, there are many interesting results in this direction, and those work are all based on Fourier analysis. But we won't have time to talk about this direction. So we're going to focus on the location of thresholds, and mostly we're going to focus on the Kahn-Kalai conjecture. Okay. So in the next part, I'm going to introduce the Kahn-Kalai conjecture, and this is a very strong conjecture. So even the authors of this conjecture said that it would probably be more sensible to conjecture that it is not true. So let's see why this conjecture was believed to be not true. And the fundamental question behind this conjecture is this: what drives the threshold? So in the next slides, we're going to examine 3 examples, and from those examples, we're going to investigate like what drives. So what drives the threshold? What drives the location of the thresholds? What determines or what affects the location of the thresholds? That's what we're going to investigate in the following 3 examples. Oh, by the way, do we have any questions so far? Okay. Then the first example. So all of the examples will be from the random graph theory because as I said at the beginning, the random graph theory is the starting point of the Kahn-Kalai conjecture. So let me introduce what was the motivating examples. So in the first example, so we are considering GMP, and our increasing property is to contain a copy of H, where H is this. And our question is, what's the threshold for GMP to contain a copy of H? And if you have taken like probabilistic combinatorics in your, I don't know, undergraduate or graduate program, then you would have seen this before. Anyway, so here, well, let's just assume that we haven't seen this before. So we are interested in the number of copies of H in GMP. So that means we are interested in this random. So the number of copies of H in GMP is a random variable. And it's not just a random variable, it's a numerical random variable. And when we want to know about a numerical random variable, then what we can do is the first thing that we check is usually its expectation. So following that step, let's check the expectation. So if we check the expected number of H's in GMP, then again, up to a constant factor. So this means we ignore constant factors. Up to a constant factor, we have n to the 4 times p to the 5. Here, n to the 4, this is the number of potential H's in GMP because H has 4 vertices. So there are roughly n choose 4 ways to pick a potential copy of H up to a constant factor. And then this p to the 5 is the probability for each H to exist because H has 5 edges. So the probability for each copy of H to exist is precisely p to the 5. And then we can easily see that this expectation tends to 0 if p is much smaller than n to the negative 4/5, and this tends to the infinity if n is much larger than n to the negative 4/5. So in this sense, we can say that this n to the negative 4/5 is the threshold for the expectation, because this is where the phase transition happens in terms of expectation. And so this expectation computation is very easy, and it gives us a trivial lower bound on the threshold. Because if we are below n to the negative 4/5, then the expectation tends to 0. So that means typically x is 0, which means or x is 0 with high probability. So that means if we are below n to the negative 4/5, then it is unlikely that GMP contains a copy of H. So by the definition of thresholds, the threshold for this increasing property must be at least as large as n to the negative 4/5. So this is a lower bound on the threshold. But in fact, we know that the actual threshold for this increasing property is equal to this trivial lower bound. So we use the second moment method to prove this, but let me not go into the details. But the lesson that we get from this example is, at least for this example, the threshold for the expectation predicts the right threshold. So after learning about this example, maybe we can dream that, oh, this easy expectation computation predicts the right threshold. But this is not true, and we're going to see that in the second example. Oh, by the way, do we have any questions about the first example? Okay, so in the second example, again, we are considering another graph, which looks like this. And notice that this H tilde is H with a little tail, if you remember what H was in the previous slide. And again, our question is, what's the threshold for GMP to contain a copy of H tilde? And again, we can start from the expectation computation, and the expectation is n to the 5 times p to the 6, and this tends to 0 if p is much smaller than n to the negative 5/6, and this tends to the infinity if p is much larger than that. So again, we can see that this n to the negative 4, n to the negative 5/6 is the threshold for the expectation. So this gives us a trivial lower bound on the threshold. So from the lesson, from the previous example, we can ask, so is this n to the negative 5/6 the right threshold? But this time, the answer is no. The answer is something much larger, which is n to the negative 4/5. So why does this difference happen? So here, what's happening here is from the expectation computation, we have we have this n to the negative 4/5. Oh, sorry. We have this n to the negative 5/6, and below this threshold for the expectation, there is typically no H tilde. So this gives a lower bound on the threshold. And then the question is, then if we are above n to the negative 5/6, do we have H tilde typically? But the answer is no. We have to have n to the negative 4/5 to have H tilde. So why is this true? This is because of the previous example. So in the previous example, we saw that so this n to the negative 4/5, this is the threshold for having a copy of H. And because H is a subgraph of H tilde, so if we are below the threshold of H, then there is no H. And because H is a subgraph of H tilde, so if there's no H, then there's no H tilde. So from this example, we learn another lesson, which is, so just computing the expectation of the given graph is not enough to find the right threshold. That's the first lesson. On the other hand, the second lesson is, as long as we look at the right subgraph of the given graph, then the threshold for the expectation for the right subgraph still gives us the right threshold. And that is actually proved by Erdos and Rennie and Bolobash back in 60s and 80s. So they showed that, roughly speaking, for any fixed graph H, the threshold for having a copy of H is equal to the threshold for the expectation of the densest subgraph of H. Here, the densest is just the number of edges divided by the number of vertices. So in this case, in this example, because the densest subgraph of H tilde is H, this, so the expectation threshold, the threshold for the expectation of H determines the right threshold for having a copy of H tilde. So yeah, okay, so this example or this theorem tells us that then we are done with all of the fixed graph containment. So whenever we have a fixed graph, we know everything about the threshold for having, not everything, but we know a way to find the right threshold for this increasing property, having a subgraph H. So we are done with the fixed graph. So the next thing that we are gonna check is then what if the given graph is not a fixed graph, but is a growing graph? So in the next example, we consider a perfect matching, where a perfect matching looks like this. So this is a collection of disjoint edges that contains all of the n vertices. So here, again, our question is, what's the threshold for GMP to contain a perfect matching? So we, of course, we assume that 2 divides n, because otherwise there's no perfect matching, but this is silly. So again, we start from the expectation computation because we learned a lesson that this expectation is very closely related to the actual threshold. And let me skip the computation, but if we go over this computation, then we can easily find that the threshold for the expectation is 1 over n. So this 1 over n gives us a trivial lower bound on the threshold, because if we are below 1 over n, then typically we do not have a perfect matching. So we can ask, then is the right threshold equal to 1 over n? But in this case, the answer is no. The truth is the threshold is equal to log n over n up to a constant factor. And in the previous example, I said, so just computing the expectation is not enough. We have to look at all of the, the densest subgraph of the given graph. But when you look at the perfect matching, then you see that there's really no densest part in this graph because all the parts look the same. So in this case, indeed, whatever subgraph we consider, we always have the threshold for the expectation 1 over n. So here, there is really this non-trivial gap between the threshold for the expectation and the actual threshold, which is log n. So then let's think about why we have this log n. So yes, and another well-known fact is that actually log n over n is another trivial lower bound on the threshold. And this is because of the fact that if p is much smaller than log n of n, then typically GMP has an isolated vertex. And because a perfect matching is a spanning graph, so if there is an isolated vertex, then of course there's no perfect matching. So in this case, the expectation was not a main obstruction, but the main obstruction is the existence of an isolated vertex. And because of that, we have another lower bound log n over n for the threshold. But I want to explain this phenomenon with the coupon collector problem. So yeah, so coupon collector problem is each box of cereal contains a random coupon and there are n different types of coupons. And the question is, how many boxes of cereal do we typically need to buy to collect all of the n coupons? And in this case, we know that the answer is n times log n. And then how does this coupon collector problem relate to the existence of isolated vertex? That's because, so in our situation, we have n vertices, and those are our coupons. And each time we throw a random edge, we regard this as we collect 2 coupons each time. And this coupon collector problem tells us that if the number of edges in our random graph is much smaller than n times log n, then typically there is an isolated vertex. So this is the lesson from the coupon collector problem. And then this number of edges much smaller than n times log n, this corresponds to our probability much smaller than log n over n, because we have n choose 2 potential edges. So this so we can explain the existence of the isolated vertex using this coupon collector problem-ish behavior of the GMP. So let me skip this example, but let me move on to the summary part. So at the beginning, I said, so our question, the fundamental question is what drives the threshold? And we have seen three examples. From the first two examples, we saw that the threshold for the expectation gives us a trivial lower bound. And the last example about the perfect matching, we saw that the coupon collector-ish behavior of GMP pushes up the first lower bound by log n. So those are all about lower bounds, and historically, in many, many interesting cases, the main task is to find a matching upper bound. And then the Kahn-Kalai conjecture, a rough statement of the Kahn-Kalai conjecture is this. For any increasing property, the threshold is at most log x times the expectation threshold. So this indeed says that this expectation threshold, which is an easy lower bound, also gives an upper bound up to this log x factor. And as I said, this conjecture is very strong. So this immediately implies historically very hard questions. And let me just introduce this question, which is called Shamir's problem in 1980s. So this was threshold for perfect hypergraph matchings, which is proved by Johansen, Kahn, and Gil in 2008. And so let me not explain, because of the time constraint, let me not explain what is a perfect hypergraph matching, but the way that the Kalai conjecture works here is, so if we compute the expectation threshold for this increasing property, then we have this quantity, which is very easy to compute. So this gives us a lower bound. And if we apply the Kalai conjecture to this lower bound, then we have an upper bound on the threshold, which looks like this. But so you see that there is this log n gap between the expectation threshold and this upper bound given by the conjecture. But this upper bound is actually the second lower bound given by the coupon collector-ish behavior of a random hypergraph. So that means we have an upper bound which matches the lower bound. So this just nails down the actual threshold for this hard question. And there is another motivating conjecture, what can I say? Motivating hard question for the conjecture, for the Kahn-Kalai conjecture, but let me skip this part. Anyway, so in general, the Kahn-Kalai conjecture is very strong in the sense that, so usually it's just very hard to find the threshold for arbitrary given increasing property, but this conjecture, if we apply this conjecture, then it just says that the threshold is in this teeny tiny window given by the expectation threshold, which is usually easy to compute. So yeah, so this conjecture is recently proved.
About this conjecture, so you have log x times, and then in the example x was n. Is this always log n, or is it log of like some important problem parameter that might vary across problems?
So yeah, in their conjecture, the parameter, the gap was log of size of the universe, but later what we proved is log of the size of, so in these previous examples, log of size of the given graph. So in the first example, when we consider the fixed graph, then this x actually means the number of edges inside in the given subgraph. So that's just constant.
Thanks.
Yeah. So that means in the fixed graph containment, there's no gap, which is already proved back in 1980 by Bolomash. And so we proved the Kahn-Kalai conjecture with log x, with replacing log x by log of this subgraph. And that recovers the theorem of Bolomash back in 1980. Okay, so now I have 4 minutes left. I don't know what I'm gonna do, but let me just introduce the expectation threshold because I haven't defined the expectation threshold. So here, the difficulty is, so in the previous examples, we consider a concrete example of a subgraph containment. So there, it was pretty obvious whose expectation we want to compute. We just want to compute the expectation of the given subgraph or subgraphs of the given graph. But in our setting, so this x is just any arbitrary universe, and then we consider arbitrary increasing property F. So there's really no symmetry here. So if F is just this random working increasing property, then it's unclear whose expectation we want to compute. So we need a careful definition for the threshold for the expectation. And the definition of this threshold for the expectation actually makes the problem hard to attack. So this is so we start from one observation. We start from a lower bound on the threshold. And so we can get a lower bound on the threshold if we can find this family G, which we call a cover of the given increasing property. And let me just draw a picture of the meaning of the cover. So let's say this is F, and a cover means this is a collection of vertices. And cover means if we collect everything above each element, then this collection of, let's say, what can I say? Let's say this is S, and the collection of this offset of S. So offset means if we have an element, S here, then we collect everything that contains the given S. So this is the meaning of the offset of S. And if we take the union of the offset of S, then this contains the given increasing property F. So this is the meaning of G covers F. And the second requirement is if we add up Q to the S for all of the S in the cover, then it must be small. And you can notice that this Q to the S is precisely, when we have S here, this Q to the S is precisely the measure, UP, of offset of S. So this basically means because G covers F, so that means if we take the union of the offsets of S, then it covers the increasing property F. And the second requirement says that the summation of each offset is small. And of course, if the summation of each subset, what can I say? The summation of the measure of each offset is small, then the measure of F itself is, of course, it's small. So this cover gives guarantees that the mu P measure of F is small. So that means this P must be a lower bound on the threshold. So if I connect this notion to our previous examples, no, I think I don't have time. So let me just skip this example and directly move on to the next part. So anyway, so this observation says that whenever we have a cover, then by considering the measure of all of the offsets, we can have a lower bound on the threshold. And then the definition for the expectation threshold is the maximum among all of the lower bounds gotten by this cover. So whenever we have a cover, we can get a lower bound by considering the measure of the offset, and then we consider all of the lower bounds given by the cover, and then the expectation threshold is the maximum among all of the lower bounds given by the cover. So this is the definition for the expectation threshold, and then finally our result is, let me skip all of the history, and this is the most recent result in this direction. So we proved the Kahn-Kalai conjecture with the size of X replaced by L of F, where L of F is the size of a largest minimal element of F. This means if we have our increasing property F that looks like this, then we consider all of the minimal elements, and then we take the maximum size. This is L of F. So for example, if our increasing property F is to contain, let's say, a triangle, then in this case, if we consider this picture, then contain triangle means our increasing property F looks like it's supported by all of the triangles, labeled triangles. And then we consider all of the offsets. So in this case, L of F is the number of edges in the triangle, which is 3. So in this case, this log L becomes a constant. So this tells us that the threshold is actually equal up to a constant factor to the expectation threshold. So one last comment. So here, what is this constant? It seems some people are interested in this constant. And in our paper, so this is joint work with Hui Pham at Stanford. In our work, we didn't try to optimize our constant, so this constant was about 1,000. But recently, I heard from Van Fu at Yale that he improved this constant to 3.998. So I think we are getting into a very good range for the constant. So yes, I think I should finish my talk now, and thank you very much for your attention.
Wonderful. Thank you. Here, I'll do a, oh, can I do a clapping emoji? Yay. Yay. Very, very nice talk. So let's open it up to the audience for some questions now. And as a reminder, we'll have some questions now, and then we can also have some questions without recording in a few minutes. So go ahead and just kind of unmute if you have any questions.
Sorry, I have a question. Is it trivial to find the maximal cover, the largest cover, or can we do that computationally?
I can't hear you clearly.
I mean the largest cover. Can we find it computationally easily or not?
The largest you mean the optimal cover?
Yeah.
It's hard. So for example, as I said, if you just look at the definition of this cover, then you see that it's very hard to compute the optimal cover because there are just so many possible covers. So if we consider, like, if we say the size of X is N, then here we consider 2 to the X, which is size 2 to the N, and then a cover is a subcollection of 2 to the N. So just theoretically, there are 2 to the N many possible covers. So it's computationally, it seems very hard to find. And I don't know, we don't have a good way to find an optimal cover. But so this seems disappointing, but the good news is we have a way to give an upper bound on the expectation threshold, and that is easy. So once we have, what can I say? So there is another parameter which is called spread. And once we find, so again, spread is given by just picking one, like, what can I say? Picking one fractional cover, then we can compute its spread. And once we have a spread, then that gives an upper bound on the expectation threshold. So that way we can easily find an upper bound on the expectation threshold. And then also we can easily find a lower bound on the expectation threshold, because whenever we have a cover, that gives us a lower bound on the expectation threshold. And if we are clever enough to find a good cover and good fractional cover, and if this lower bound and the upper bound given by the spread matches, then that just nails down the expectation threshold up to a constant factor.
Yeah, got it. Thank you.
Any more questions with the recording on? Okay, so I will